Hi. So we are already in the geometry plot in the CFD fluent file. So what we need to do is first make the converging diverging the nozzle. So for that, first we are changing the units to millimeters, and so we use a polyline feature to draw a rough sketch of the converging diverging nozzle, and that's what is being shown in the video right now. So after this is done, we need to symmetricize it about an axis. So that's what is being doing. So we select the axis and with the points that needs to be symmetric. Sorry about that. So we're doing symmetricizing again for all the points. So once it's symmetricized, we need to give in the actual dimensions, which is what we will be using the length distance tool to first to define the lengths for the different lengths. So L1 will be the throat throat distance, and L2 is the inlet, L3 is the outlet, L4 is the length, the slanted wall length, and L5 will be the distance between the converging, diverging inlet and outlet nozzles. So we're defining the throat nozzle to be 15 millimeters, and the inlet to be 30 millimeters, outlet to be 45 millimeters, and the slanted wall height is about 45. Let's just take that for an instance, and the distance L5 is going to be about 80 millimeters. Okay, once this is done, we need to generate the sketch. So we do that by going to concepts, surface from sketches. We select the sketch, we apply the sketch, and we generate. That's okay. So once the sketch has been generated, we need to split the parts because converging diverging is two different parts. So we do that by drawing a line, and after we draw the line, we're gonna go to tools, face split. We select the face, we apply, and we click on the geometry. Basically we're going to be splitting it about the line. We apply and then generate. So once now this is being split into converging, diverging, like we've split the parts. Now we will further split the parts, which we draw a line again, two parallel lines. So to make it parallel lines, we use a constraint called parallel, to parallelize the lines. Once we parallelize the lines, we input the distance. We want to keep it equidistant from the middle line. So we're going to take both the distances to be about 10 millimeters approximately. So once this is done, we will be basically doing the face split again, but about the converging nozzle and diverging nozzle separately, and that's what is being shown right now. So we do the same procedure, split the face parts first about the converging nozzle, and then now we're doing that for the diverging nozzle. So once this is done, we exit the design modular phase and we'll be moving on to the mesh.
Okay, now we're going to start creating the mesh. Double click the mesh part. Wait for it to generate. Then we click and change the view to the front view. Press mesh and go to insert and put method. Select the mesh, press selection, apply. Now select the vertical side. Press Ctrl and press the vertical sides. Right click, insert, and go to sizing. And check the element size, change the number of divisions, and change the number of divisions to 30. Now select the slanted walls, press all of them by using Ctrl. Insert and again press sizing. Again we need to change the element size from to number of divisions. Put it to 20. Then press mesh and then we update the mesh. We press the face, press each face of the right click, insert and apply face meshing. Press the mesh and we update the mesh again. Next we click the inlet and we change the name, press the create name selection and change the name to inlet. Press OK and then we go to the outlet, right click, create name selection and change the name to outlet. Press OK. Now select the slanted walls. Then right click, go to again the create name selections and change the name to slanted walls. Press OK. Go to the name structure, click, press Ctrl and press the three of them. Go to file and close meshing. Next we have to update the mesh. Next we go to the setup, double click setup, press OK. Just wait for it to load. Okay, now we change it, go to general, change it to density based, models, and press energy and turn energy equation on. Go to materials, go to air, we go to change the density to ideal gas and viscosity to Southern. and press OK. Now we go to boundary condition, press inlet and change into pressure inlet, and we change the gauge total pressure to 3 into 10 raised to 5. Now we press outlet, go to type and change it to pressure outlet. Now we go to reference values, press compute from and press inlet, and go to reference zone, press solid surface body, go to monitors, we press create, press drag, we print to console plot, and then press slanted walls and press OK. Now we go to solution initialization, press standard initialization, compute from the inlet, and now we initialize. We press run calculation, change the number of iteration to 700. We press calculate. And we see how the solution is being formed. Now press OK as the calculation is complete. We can see the convergent history, the number of iterations, and the CD plot. Now let's go to graphics. Press contours from the graphics section. Press fill. And select all. Display. We see a plot. Next. Display, and we see the pressure graph, and from the pressure graph we can see how the pressure is high at the inlet and low at the outlet. And now we change to velocity and the Mach number, and as we see, the Mach number is least at the inlet and maximum at the outlet, and at the throat it's around 1. Now we go to the plots, press the XY plot, double click it, and we change the Y-axis function. We press slanted walls, we plot, and we see the plot. We see how the static pressure is maximum at the inlet and minimum at the outlet. Next we change to velocity and Mach number, plot, and we'll get the Mach number plot. Now we close the Fluent file.
Okay, so we open the results section and we'll be using the front view just to for a clear view. Then basically the result section is to plot a streamline function and to see how the streamline is going from the inlet to the outlet. And so we define the number of points to be 75 and start from inlet, and we can see how it's changing, and we can also change the number of plots from 75 to 150 and see again how the function is changing. And lastly, we can run like a nice animation to see how the streamline function can go through. When we run the animation, we can see how the streamline is actually going to flow. And that's the end of the video. Thank you.